In this video, we're going to look at integrating using a natural log antiderivative. Let's recall that when you have an integral of specifically a fraction where you have some terms in the denominator, it could be one term, it could be two or more, but whatever you have in the denominator, if its derivative is the numerator, then this is the perfect candidate for a natural log antiderivative. Specifically, it'll be natural log of the absolute value of your denominator plus your constant of integration if it's an indefinite integral. So let's remember this formula going forward. Our first example today was the integral of 1 over 5 minus 7x dx. The denominator, if you were to take its derivative, you would get negative 7. Well, we don't have negative 7 in the numerator, but if it's a scalar value, you can multiply in the actual derivative. And again, that's just if it's a number that you're missing. So we have our derivative of negative 7. I'm going to multiply it in, but to keep it balanced, I'm going to multiply by negative 1/7. Why is that? The numbers you see here in the plum color, if you multiply those, you get your 1. So it's just a well-crafted 1. But it had a mission because this denominator, its derivative, is now in the numerator. And we see that anytime our denominator has its derivative as the numerator, then it qualifies for natural log as its antiderivative. So this will be negative 1/7 times the natural log of the absolute value of your denominator. Now, if by chance you get a denominator that can't be negative or 0, like say this is x squared plus 3, then when you put x squared plus 3, you don't necessarily have to have the absolute value. It's just smart to use the absolute value to cover yourself. In the second example, we have the perfect candidate. Check out your denominator, x cubed plus 6x. What's the derivative of this denominator? It's 3x squared plus 6, right on the money. This is a perfect case of denominator with its derivative in the numerator. So this goes back to that formula of u prime over u, and the antiderivative is natural log of your denominator. So natural log of x cubed plus 6x plus your constant of integration. In our next example, we have the integral of x squared minus 2 over 2x dx. Now for this one, it's a little awkward because we can tell it doesn't immediately qualify. Our denominator 2x only has a derivative of 2, so we clearly don't have just a 2 as our numerator. But we do know that if we have a common denominator, we can split terms from the numerator into separated fractions. Specifically for this one, x squared over 2x minus 2 over 2x dx. And over to the right, that's all I've done is I've split the numerator up and left the common denominator underneath each fraction. Simplifying, x squared over 2x is x over 2, or 1/2 x, minus the second fraction, the 2's cancel, and that leaves 1 over x. I went ahead and split this into two integrals. It's totally okay to do that. With this minus sign in the middle, you can subtract two separate integrals. The antiderivative of 1/2 x is 1/2 times x squared over 2, which is 1/4 x squared. The second integral, we have a denominator of x its derivative is 1, so that qualifies as an antiderivative using natural log. So that's minus natural log of the absolute value of your denominator plus your constant of integration. So our general antiderivative is 1/4 x squared minus natural log absolute value of x plus c. In the last example, we had a monomial for a denominator. In this one, we have a binomial for a denominator. The denominator, x minus 1, its derivative is only 1. Clearly not this numerator. Well, let's chop away at this using long division. So x minus 1 is our divisor. 2x squared plus 3x minus 7 is the dividend, and that'll go underneath your long divide bracket. Since you don't do long division just a lot, I want to remind you the steps for it. So we'll take our first term underneath, divide it by our first term outside. 2x squared divided by x is 2x. Now you take 2x times both terms of your divisor. That's 2x squared minus 2x. 2x squared minus 2x. In long division, you subtract those values, so you basically just swap the signs. That positive term goes negative, this negative term goes positive. Vertically, you combine like terms. 2x squared minus 2x squared is 0. If the first column adds up to 0, then you're doing it right. The next column, 3x plus 2x, that's 5x. And then you drag down the next term, minus 7. Then you start the process all over again. First term underneath divided by first term outside. 5x divided by 1x is 5. 5 times the divisor is 5x minus 5. 5x minus 5. Reverse the signs of your terms. Combine your like terms vertically. 5x minus 5x is 0. Negative 7 plus 5 is negative 2. So the purpose of the long division is to take this big fraction and break it down into simpler terms. Specifically, the quotient, 2x plus 5, minus the remainder, which is negative 2, over the divisor, x minus 1. Start at the top and go clockwise. That's how you translate all that long division. Taking our antiderivatives of the first two terms, that's x squared plus 5x, minus, I went ahead and pulled this numerator of 2 out because it's a scalar multiple, so minus 2 integral of 1 over x minus 1 dx. Now, the reason I held off on this one is because this one does qualify for a natural log antiderivative, because if you take the derivative of this denominator, you do get a 1. So that's minus 2 natural log absolute value of your denominator, x minus 1. And don't forget your plus c for constant of integration. I hope this video helps out. If you have any questions, reach out by phone or email. If you're on campus, stop by the office, and I'll do my best to help you out.